Hello again. So this is question 9. And for question 9, we have an application of the Thevenin equivalent circuit. So in this circuit, it's an unbalanced bridge, okay? And in part A, we have to derive the Thevenin equivalent circuit between nodes A and B, excluding R5. So R5 is actually our load. So we are analyzing what's the equivalent circuit using Thevenin's theorem. For part B, we have to uh, using the Thevenin circuit and with R5 equals to 1K, calculate the current flowing through it. So it's just this current here that we have, I, right? This current here. Then on part C, if R5 is considered a varying load and it becomes 10K, what would be the new current through it? So we just have to change the value of R5 and then calculate the new current, okay, using again the Thevenin circuit. And then on D, comment what's the utility of Thevenin's theorem in such a scenario of analysis under varying load conditions, okay? So let's start it. Um, so for the Thevenin equivalent circuit, we first have to get rid of we can calculate the Thevenin resistance, and for that we have to basically turn the voltage source off, and we do that by basically short circuiting that voltage source, so it becomes a short circuit here, right? And because we are calculating the Thevenin equivalent circuit seen from this terminal A and B, we basically remove this R5 here, so we take it off. And then the circuit that we are left is something like this. So we have terminal A here that I'm going to draw, right? So this is A. We have terminal B here. And then we have a resistor here in series with another resistor here, another resistor here, in series with this one here, right? But because these two nodes here, they are connected, right? So the elbow go to the ground, right? Because we short circuit here the voltage source that we had on this node, and here it was already connected to the ground. So this circuit, it becomes just, so if you want to calculate the Thevenin resistance of this circuit, it is just the sum of the parallel between, so let's see what's the values of the resistors that we have. So here is 2K, here is 4K, here is 3K, and here is 5K, right? So the Thevenin resistance of this circuit is just 2 in parallel with 4 plus 3 in parallel with 5, right? So this is the same as, so let me calculate, RTH equals to 2 times 4 divided by 6, right? 2 times 4 divided by 2 plus 4, which is 6, plus 3 times 5 divided by 3 plus 5, which is 8. And this gives us a Thevenin resistance that is 3.283 kilo ohms, right? So that's the Thevenin resistance. Now, for the Thevenin voltage, we have to insert the voltage source here back in the circuit, right? And then we need to calculate what's the voltage, right? What's the voltage across this node A and node B, right? So if we uh, look at this circuit the way it is here, it's basically because we have like an open circuit between A and B, right? So between this node here, so let me just say between this node here and this node here, we have this 10 volts applied, okay? Right? Because we have 10 volts here and we have 0 here. This is an open circuit between A here and B here, right? So we have 10 volts applied to these 3K and 5K, but we also have 10 volts applied to this 2K and 4K up there. So to calculate the open circuit voltage, which is this voltage here between nodes A and B, we just have to basically we have to calculate VA here, which is the same as the voltage applied to this R1, right? Or sorry, the voltage applied to this R4 here, right? And the voltage VB, which is the same as the voltage applied to this 5K here. So we just need to use voltage dividers, right? So for the first voltage divider to calculate VA, we have the 10 volts applied, then we multiply that by the 4K, which is this resistor here, divided by the same 4K plus the 2K, okay? And that gives us 6.67 volts. Now for VB, we have the same 10 volts applied, but now we have to calculate the voltage across this 5K. So it's 5K divided by 5K plus 3K, and that's 6.25 volts. Okay, now the Thevenin voltage is the same as, VA minus VB, which gives us, so if we take this one's the values that we just calculated, 6.67 minus 6.25 volts, this gives us 0.4167 volts, right? So this is the Thevenin voltage. Now, since we know the Thevenin voltage and the Thevenin resistance, we can build the Thevenin equivalent circuit, which is the voltage source in series with this Thevenin resistance, right? So this is 0.4167 volts, and this is 3.2083 k ohms, right? Now for part B, we have to insert the R5 here, and this R5 is 1K. So how do we calculate the current that's flowing through this load? We just take, so the voltage divided by the series of 3.283K with the 1K. So this current I is going to be the same 0.4167, 67 divided by 4.2083K, and that's equals to 0.9901 microampere, right? Now for part C, we have to calculate this current again, but now the value of the resistor just changes by 5K, right? So in this case, I is equals to 0.4167, so this is B, this is C, divided by 5K plus 3, it's 5 or it's 10. Let me double check up there. So it's 10K, right? So sorry about that. So it's 10K here divided by 10K plus 3, so it's 13.283 kilo ohms, and that's equals to 0.3154 microamperes. So you see that once we have calculated the Thevenin equivalent circuit and we change our load from 1K to 10K, to calculate the current that's flowing to that load, it's just a matter of changing this resistor here, right? So this simplifies the analysis. Now for part D, it basically asks us to comment on the utility of this Thevenin's theorem in such scenario of analysis under varying load conditions. So one thing is that if we keep changing our load, we can easily calculate the current and the voltage applied through that load if we have this simple circuit, because it's just like one of the most simple circuits that we might have, right? It's just like a voltage source in series with a Thevenin resistance or just a resistance and our load, right? And another advantage is that if you remember from the maximum power transfer theorem, uh, we know that if we have like a configuration like this one here from the Thevenin's equivalent circuit, right? We know that for circuits that we have only resistors, the maximum transfer of power to the load will occur when this load has the same resistance as the Thevenin resistance. So if you want to have like maximum power being transferred from this voltage source to the load here, the resistance 10K actually should be equals to this 3.2083K. That will give us the maximum power, power transfer to the load. If you remember, we would have something that looks like this, right? So this peak here, if this is the resistance and this is power, right? The maximum power here occurs exactly when our R load is equals to the Thevenin resistance. Okay, so that's that's also one of the importances of using Thevenin's theorem. Okay, so that's it for this problem.